Good day, I'm Norman Wahlberger, and today we're looking at Boolean algebra and set theory. So we're having a look at the history of logic, and in the latter part of the 19th century, Boole started to mathematize logic. And then his algebra morphed a little bit, and we're going to be talking about that story today, morphed into what's now called Boolean algebra, which ended up having a major impact into the 20th century development of circuit analysis. But originally, the Boolean algebra was more oriented towards the arithmetic or algebra of set theory, finite set theory. So we want to talk about that today. And I want to do it in the spirit of the algebra or algebraic approach that we've been looking at, where we start with just zeros and ones, and we have an arithmetic with zeros and ones built up by Boole. So we have two quantities, P and Q, and here are the possible values, 0 and 1. There's four possible values for these quantities, P and Q. And then here are the various operations that the Boole's algebra originally is built on, the addition and the multiplication. And these are just addition and multiplication mod 2, where we're working in the by field with two elements. So this is the original algebra of Boole that we've been talking about. And today we want to talk about a variant of that called Boolean algebra, where the operations are a little bit different. So instead of having the addition here, which is sort of the exclusive OR, we have the ordinary OR operation. So this is, you might say, P or Q. And when these are 0, we get 0, here we get 1, here we get 1, and here we get 1. So notably the difference between the OR and the exclusive OR is just in this position right here. The other operation we could call AND, which is really the same as the multiplication in the Boole algebra situation. So I've got a wedge going this way. 0, 0, 0, 1 are the values. And then there's another operation of negation. Okay, so if we just look at the P values here, we negate P, or sometimes called not P, then we get 1, 1, 0, 0. So with Boolean algebra, what we do is we concentrate on these operations and not so much on these ones. And often in the treatment of circuit analysis, these operations, instead of having wedges and joins, they are often presented also with additions and multiplications. So that it's easy to get actually confused between additions and multiplications in this Boolean algebra context and the original mod 2 context of Boole. So to try to minimize that confusion, but still to have it available for us, we might use addition with a circle addition and circle multiplication to represent the union here and the intersection. So this thing here, this operation, this could be thought of as the Boolean addition, and this one here could be thought of as the Boolean multiplication. And another notation that's sometimes used for the not operation is to have some kind of bar like this in front of P. So today we want to look at the Boolean algebra and how it arises from the algebra of sets, actually quite naturally. Now it's my position that the algebra of Boole is actually probably a little bit more useful and more fundamental than Boolean algebra. Although I don't want to be too dogmatic about that, but my orientation is going to be in the direction of the algebra of Boole. And so one of the things that we're going to be doing is converting things from the Boolean algebra to the algebra of Boole, and I want to show you how the arithmetic there allows us to solve problems in the Boolean algebra situation. So to make that happen, it's useful to have these ways of transferring from one operation to another. So the union operation, P union Q, can be written in terms of the addition and multiplication, the mod 2 Boole operations, as P plus Q plus PQ. So it's really the sum of the sum and the product. And the wedge here, which is P and Q, this is really the same as the product P times Q. So there's no difference at this level, but there is a little bit of a difference here. And in terms of the not, the negation, not P is the same as 1 plus P in the Boole algebra situation. So a little bit of an exercise for you to express conversely P plus Q and PQ in terms of the Boolean algebra operations. Okay, so now let's introduce some of the figures that were involved in this shift from the algebra of Boole originally, that George Boole initiated, to the 20th century development towards Boolean algebra. So two important figures there were John Venn, who was working in set theory, and he lived from 1834 to 1923. And Charles Sanders Peirce, American mathematician, philosopher, kind of all-around thinker, from 1839 to 1914. So these two men were probably prominent in shifting the direction of this algebraization of logic towards Boolean algebra. The Boolean algebra was then sort of put on a firm abstract footing by Edward Huntington, who lived from 1874 to 1952. So let's talk about finite set theory. We've already talked about data structures, and we've seen that sets are one of the four important types of data structures, along with lists, multisets, and ordered sets. And from my point of view, set theory, when restricted to finite sets, which are explicit and concrete and consist of mathematical objects, is a perfectly beautiful and important and useful branch of combinatorics. So we have combinatorics, and set theory is a part of combinatorics, along with multi-set theory and list theory and many, many other things. Okay, but I oppose this idea that set theory is some kind of, magic foundation for all of mathematics. It's completely wrong thinking. Okay, it's an important ingredient, but along with other ingredients. And in particular, we have to have a constrained view of things. We don't want to just be opening the door to any kind of phraseology to invoke sets of all kinds of things. It's a very serious mistake to think about that. So I do want to point out that my criticisms of set theory are not directed towards finite, concrete, explicit set theory. And that's what we were talking about here, that Venn was interested in. So let's have a look at how the Boolean algebra fits with this very classical, very concrete, very finite set theory. So the idea is we're considering very explicit mathematical objects, and we imagine that we have a universal fixed set, say U. Okay, so it's a finite set, and it's very explicit and concrete and consists of mathematical objects of a certain kind. And inside here we have certain subsets which are of interest. So for example, in this diagram here, we have U represented by this box, and then we have three sets, A, B, and C, represented by these circles. And the circles overlap, and the various overlapping regions define and illustrate various kinds of subsets that are created or can be created from these three original sets. So these days this is called a Venn diagram, but probably actually the idea of such a diagram goes back to Euler. But if we named everything that Euler discovered after Euler, then too many things would have the name Euler to them. Okay, so what do we see in this picture here? Well, in red, you see the union of A and C. A union C. And in the Boolean algebra language, this union is replaced with a wedge. Okay, that's like an operation. A wedge C there. That's the union. And maybe we could also say join, right? We're joining the two sets. And the other operation is an intersection. So there's B and there's C, and then in green there, you see inside here, this is representing the intersection of B and C, which in the Boolean algebra situation is represented by this upside down wedge. Maybe that's like a V, and this is a wedge, you might say. This is like a meet intersection. Okay, so these are physical representations of basic operations of sets, which connect directly to our two operations in the Boolean algebra situation. And this is really the motivation of Venn to work with this Boolean algebra, because it's reflecting what happens with sets and their interactions. So these Venn diagrams allow us to illustrate some basic laws. For example, De Morgan's laws. And here they are. The first one is that if you take the complement of A union B, that's the same as the complement of A intersect the complement of B. So let's illustrate that now with a Venn diagram only containing two sets A and B inside the universal set. Okay, so here in red we see A union B, the things that are either in A or in B, or possibly in both. So this is an inclusive OR. And here A union B complement, these are all the things which are not in A union B. So it's everything outside this one here, but still inside the universal set, which is represented by the box. So that's the set there in green. Okay, so that's representing the left-hand side. What about the right-hand side? Well, over here, there's the set A. So here in green dots, we see the complement of A, everything that's not in A. And over here, there's B, and in green on this side, we see everything that's in the complement of B, everything that's not in B. So if we take the intersection of not A and not B, the common dots here, well, what are we going to get? We're just going to get the things which are outside of A and B. So this thing here, if we look at the intersection here, is the same as the intersection of the complement of A with the complement of B. So sort of illustrating Morgan's law, this one here. And the other law, which is just like it except that the roles of the intersection and the union are interchanged, is that the intersection of A and B, if you take the complement of that, that's the same as the complement of A union the complement of B. So let's have a look at that again. Here's A and B, and there in red is the intersection of A and B. And then its complement is going to be everything outside that, represented here. Okay, there's the intersection, and everything outside that is all the green dots. And the claim is that this is the same as the union of these two sets here, the complement of A, the complement of B. If we take the union of those, we should get this thing here. Is that the case? So if we take everything that's either in here or in here, getting the union, we get everything except the things in the common middle. So yes, indeed, we can see that that's the same as A complement union B complement. Okay, so we can see that these Venn diagrams allow us to see the validity of simple kinds of Boolean representations having to do with sets and unions and intersections. So in the same spirit, let's look at the two distributive laws for set theory. So these are very important laws. They mimic each other, and they are a little bit like the distributive laws in arithmetic. So the first one is A union B intersect C is equal to A union B intersect A union C. So let's illustrate that now with the Venn diagram with three sets, A, B, and C. So what we see here is A, that one there, union the intersection of B and C. So the intersection of B and C is exactly this thing here, this wedge here. And so the red here is the union of A with the intersection of B and C. Okay, and we want to convince ourselves that this is the same as the intersection of A union B and A union C. So let's see if we can imagine that. Might do it on the same diagram. So A union B, what would that look like? Well, that would be, A union B would be everything that's inside there. And A union C would be everything that's inside, maybe I'll dot it, A and C. Okay, so there, dot is A union C. And we're supposed to take the intersection of those two things, the things that are common to both of them, and you can see that that's exactly the red set that we have on the left-hand side. The other distributive law, A intersect B union C equals A intersect B union A intersect C. just obtained from the first one by interchanging the unions and the intersections. Okay, A intersect B union C. Where is that? So here is A, and B union C is all of B and C there. And the intersection of those two things is the green stuff there. And why is that the same as what's on the left-hand side? Well, A intersect B, that would be A intersect B, that's that part there. And A intersect C is this dotted stuff over here. And we're taking the union of those, and indeed the union of this one and this one is the green set that we had on the left-hand side. So the Venn diagrams allow us to see the validity of this law, or these laws, and here are the just rewriting of the same laws using the Boolean V's and wedges instead of unions and intersections. So I want to have a look at one of these distributive laws, and I want to show you a standard way of proving or illustrating this law via truth table kind of argument. And then I also want to employ the algebra of Boole, which is what we're really interested in, and to show you an alternative way of thinking about the same thing algebraically. And hopefully this will also bring the connection with the logic and the set theory together. Okay, so let's look at this distributive law here, and I've just rewritten it in terms of wedges and V's. Okay, there it is there. And we want to kind of prove that this is going to be true no matter what sets A, B, and C we have. Okay, so we can do that in a truth table kind of fashion. And what we do is we create A, B, and C here, and we create various possibilities for inclusion in A, B, and C. So basically we write down all the binary possibilities, all the 8 different ways of assigning zeros and ones to A, B, and C. It'll be 2 cubed, or 8 different ways. And you can think about each one of these as sort of representing an element in the Venn diagram. Okay, so this here, for example, this row would represent an element which is not in A, but which is in B and which is in C. Something that's in B and C, but not in A. Okay, and so this row is looking at such an element and asking, what kind of properties does it have? So here I've written again what we're trying to prove, and what we're going to do is we're going to basically apply the logical rules for the the Boolean operations here. Okay, so let's see what we get here. So I'm not writing all the values, so I'm not writing B and C here just to make the table not so complicated. But let's start with this term here, right? So this is B and then a wedge C. So what does this mean? This is like the intersection of B and C. At the level of a Boolean operation, this is like an and. These are the things which are both in B and in C. Okay, so let's look at the possibilities. So if an element is not in B and not in C, is it going to be in the intersection? No. What if it's not in B but it is in C? Is it in the intersection? No. How about if it's in B and not in C? Is it in the intersection? No. What if it's in B and it's in C? Is it in the intersection? Yes. Okay, so we have a 1 here, and this is just the operation of P wedge C in our previous language. Okay, I've copied the values of A here, and now this left-hand side is an expression involving these values of A, and these values of B intersect C. And the operation is a union or an OR. Okay, so if we have something which is 0 over here and 0 here, and we're taking OR, so 0 or 0 is 0. 0 or 0 is 0. 0 or 0 is 0, and 0 or 1 is 1. So these are the various values for this left-hand side, depending on the 4 possible values that we're looking in the first half of the table up here for A, B, and C. And on this side, we look at A union B and also A union C. So if we look at just the A and B values and look at A union B, we're going to have a 0 or a 1. 0 or 0, 0. 0 or 0, 0. 0 or 1, that's 1. 0 or 1, that's 1. How about with A and C? So 0 or 0 is 0. 0 or 1, it's 1. 0 or 0, it's 0. And 0 or 1 is 1. Okay, so having now these values, this is telling us that we have to take the AND operation between those. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 1. And now these red numbers represent the cumulative values of the left and the right hand side for these 4 possible inputs situations, and we see that in each of the cases they are equal. All right, so yes, we have equality between the left and the right hand side for all of these 4 inputs. And I might leave it to you to check, it's pretty easy, that for these other 4 possible inputs we also have a similar kind of situation. In fact, we'll have ones along all possibilities, so yes, this is true in all possible cases. So this is a general strategy that if we had some more complicated Boolean relation, we wanted to determine whether it was true or false, then what we could do is we could go through all the possible values of zeros and ones to all the constituents and make some truth table like this and sort of look at all the possibilities, employing all the time our understanding of the operations of these unions and wedges on zeros and ones. So we're working in the Boolean algebra with those operations. Okay, so I want to now show you the same argument, but from an algebra of Boole perspective. Because I'm trying to persuade you that actually the algebra of Boole is in some sense a simpler and more powerful algebra than Boolean algebra for many applications. Even for this kind of set theory kind of business. So if you're teaching circuit analysis to electrical engineers, I want you to consider revamping things a little bit and moving away from Boolean algebra towards the original algebra of Boole. Okay, I know it's a big ask, but I want you to think about that. Okay, so let me illustrate how things go. So I recall that the Boolean algebra operations of the union and intersection can be represented with the algebra of Boole operations of addition and multiplication. Those are the mod 2 operations. Okay, and here's how we do it. So P union Q is P plus Q plus P times Q. And P intersection Q is the same as just the product of P and Q. So converting here is not a problem. Converting here is just a little bit of something. Instead of just having an addition, we have an addition plus the product. Okay, so we're going to take the distributive law that we just had and convert it from wedges and unions into additions and multiplications. So let's start with A union B intersect C. Okay, so the B intersect C can be expressed as just B times C. So we have A union B times C, or A V B C. Now, how do we convert something like this? It's like a union or a V. Well, according to this, we have to replace it with the first term, the second term, plus the product. So here's A plus BC plus the product of A and BC. And we know things are associative, so I'm not going to bother with any brackets. So this is a algebra of Boole representation for the left-hand side of this distributive law. Now let's have a look at the right-hand side, which is A union B intersect A union C. Okay, A union B, exactly up here, is in the algebra of Boole, A plus B plus AB. And similarly, this is A plus C plus AC. And this intersection is just the product of those two things. Okay, now we're doing the algebra of Boole. So we're going to expand using the distributive law. A times A is A squared. A times C is AC. A times AC is A squared C. And then B times A is BA, and then we have a BC, and then we have a B times AC. And then we have an AB times A, an AB times C, and an AB times AC. Just using the distributive law. Now what? Well, we're going to simplify this now. And we're going to simplify it because in the Boole algebra, in the algebra of Boole, x squared is always equal to x. That's one fundamental thing. The other fundamental thing is that x plus x is always 0. So let's do the x squared equals x first. That means we can replace the a squared with just an a. This is the same. The a squared here just becomes an a. Get ac. This is the same. This is the same bc. This we can just rearrange it as abc. And then over here, what's this? Here's an a squared b. That's the same as ab. And then another abc. And then here the a squared's replaced with a, so we get another abc. Okay, now we look at simplifying this. What can we do? Well, here's an AC plus AC. It's like x plus x. That's 0. So it's gone. There's an AB or BA. And there's another AB over here. So this one and this one combine to give you 0. We still have a BC. So let's record that. And then there's an ABC here and another ABC there. It's another x plus x equals 0. So they cancel together, 0. But we finally have another ABC left over. So altogether we get A plus BC plus ABC, which is the same as what we got up here. So yes, indeed, this right-hand side is equal to A union B intersect C. And so we've proven this distributive law now without a truth table kind of argument, just using algebra. Very powerful tool. So now we're going to move into the 20th century. We're going to see how this Boolean algebra, first of all, was sort of abstracted by Huntington, and then how Claude Shannon introduced it into the analysis of circuits. And we're then going to be able to say new things about circuit analysis from this algebra of Boole point of view. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.